Okay, so then for example 3 and example 4, I think, these are just more algebraic properties using the different powers. So it says express log base 2 of this quotient as a sum or difference of logarithms, express the powers as factors. So just another way to do kind of what we did before. I see this kind of question is more of a domain kind of question, like finding domain, because remember it's always a positive value within that square or within the log function. So I think the first thing I do is say, okay, this is log base 2 of x cubed minus log base 2 of x squared minus 9. I break that up. And I can see this 3 could come in front because it does express the powers as a factor. So 3 log base 2 of x minus, and then I notice that what's inside this log actually factors to x minus 3 times x plus 3 is a difference of squares. So I could then break up those factors into a sum, but remember it's under the influence of that negative, so I would be distributing that as I go along. So that would be the part where I think students might make a mistake if I had to anticipate that. So minus log base 2 of x minus 3, and then minus log base 2 of x plus 3 because I distributed the negative. Okay, so I have the equivalent expression as a difference or sum of logs and powers as factors. Okay? And number 4 just goes backwards. So we're taking these things, I want to combine them. And I also notice that there's a lot of factoring that can go on too. So I have a difference of logs, so that means I can put these two things. It's kind of, all right, this whole fraction divided by this whole fraction. And so that's like maybe my first step. And I might factor as I go too. So log of this guy, so maybe I won't factor just yet, x squared plus 3x minus 4 divided by x squared minus 9 divided by that guy, x squared plus 5x minus 6 over x plus 3. So all that's in a very complex, right? Very complex logarithm. I have this value divided by this value. It's a complex fraction. So when we have a fraction that's within a fraction, we can multiply by the reciprocal. So let's rewrite that, or let's think about that as log of this top part, x squared plus 3x minus 4 divided by x squared minus 9 times the reciprocal of this, x plus 3 over x squared plus 5x minus 6. And I mentioned about factoring, it's going to be a smart thing to do to help reduce this. So log of, so this would be like x plus 4 times x minus 1. This is x plus 3 times x minus 3. Here's another x plus 3, and this could be x plus, 6? And x minus 1. And so then we just look for common factors. So I see an x minus 1, x minus 1, x plus 3, x plus 3. And that's it. So then I would simplify that to maybe log of x plus 4 divided by, I could just say like x minus 3 times x plus 6. Okay. And whether or not you distribute that or not, multiply it, your choice. Okay, so then the last example, and I alluded to number 5, like one of the rules we would actually see in part E from the previous video. So when you recognize you have same powers, like right away I recognize, oh, look at 36 and 25. That's really suspicious. Those are both perfect squares. So I could do the 1/2 power, and I get an equivalent answer. So like the 1/2 of the square root of 36 is 6, the square root of 25 is 5. So I know right away that x would have to be 5. And again, if you're not too familiar, you could rewrite that as log of 25 over log of 36, which is log of 5 squared over log of 6 squared the 2's come down. I mean, we're really just proving this. 2 log 5, 2 log 6. So the 2's cancel. And so I have log 5 over log 6. And you just put it back together. That's your base of what you're taking. So log base 6 of 5. That base goes there. That quotient goes there. So it kind of just proved that, oh, you could do the same power since exponents are the inverses of logs. It's just sometimes those powers are tricky. There won't maybe not as obvious as a square root. But any power works. Any power. So then I could look at part B and think, well, wait a minute. I might not recognize a power initially until I realize that 0.1, that's 1/10. That's 10 to the negative 1. That's a power. So if going from here to here, I applied the negative 1 power, then I would do the same power to this base. So the answer would be 3 to the negative 1 power. So x would be 3 to the negative 1 power, which is 1/3. And it's okay to have the base of your log be a fraction. It just can't be a negative number, and it can't be 0. So then I'm seeing things here that are perfect cubes. So like right away I might reduce this to because I know 8 is 2 cubed and 27 is 3 cubed. So this is at least log base 2 of 3. And then I'm trying to get a 4, so that could be squared. So log base 4 of 9, therefore my x would have to equal 9. So this one, very similar to the one above. It's just, again, recognition. 0.2 is 1/5. That's 5 to the negative 1. So 5 to the negative 1. So basically I'm doing the negative 1 power to this. So therefore I better do the negative 1 power to that. So it's 2 to the negative 1. So x is 2 to the negative 1, or 1/2. Okay, so look at part E and part F. Okay, let's see. So 625. Okay, so think about, so 5 squared is what? 25, and square that again is 625. So this is 5 to the 4th. So I'm raising this to the 4th power. So I need to raise this also to the 4th power. So 4 root 2 is a quantity to the 4th power. And so, well, 4 to the 4th power would be 16 squared, which is 256. And then root 2 to the 4th power is real, so it's root 2 times root 2 times root 2 times root 2, or just 2 squared. So we have an additional 4. So I have 256 times 4, which I believe is 1024. And then let's see, the last one, so it's sort of interesting because, so 4 root 2 we wouldn't initially think is a power of 2, but it is. Because obviously I have a 2 here and I'm trying to get to 4 root 2. Well, 4 root 2, this is 4 is 2 squared, and root 2 is 2 to the 1/2 power. So you have 2.5 powers. So it looks like I raised this to the 2.5 power, or the 5 over 2 power. So that means that I need to, in order to go from here to here, I need to take that, basically, I need to figure out 100 to the 2/5 power. Because think about that. This is 2 to the 2.5, or 2 to the 5/2 power. Right now, 4 root 2 is 2 to the 5/2 power. This 100 is some number to the 5/2 power. So to undo that, to go from this to this, you're technically imposing the 2/5 power. Because if I raise this to the 2/5 power, it would cancel by reciprocals and it'd be a 1. So I need to raise this to the 2/5 power. So I need 100 to the 2/5 power. And if it doesn't simplify, I could probably leave it 100 to the 2/5 power. And how do you interpret this? Well, you square what's in here and you take the 5th root. So I could say it's the 5th root of 100 squared. 100 squared, which is 10,000. So I could say it's the 5th root of 10,000. Or I could leave it as 100 to the 2/5 power. I don't really care at this point. And in order to simplify this, I'd be looking for perfect fifth powers. Well, 1 to the fifth power is 1. Okay, that's irrelevant. 2 to the fifth power is 32. Doesn't divide into 100 or 100 squared. 3 to the fifth power is, I think, what, 343? That doesn't divide there either. 4 to the fifth power is 625. That I don't think goes in perfectly. But again, I'm more interested in applying powers than necessarily simplifying your roots. Okay, so that's that.